Yeah, welcome. So the topic we'll be discussing in this lecture is first order logic. So we are discussing about logical agents. In the last lecture, the last one or two lectures, we have discussed about propositional logic. Now we'll be moving on to the next level of logic, which is called as first order logic. So why we are discussing first order logic when we already discussed about propositional logic? The answer is actually propositional logic has less expressive power. Everything cannot be expressed using propositional logic, whereas first order logic has better expressive power than propositional logic. So now we are moving on to first order logic, right? So basically, if you see propositional logic, it is confined only to facts. It cannot deal with objects, and it cannot connect the relationship between objects. Whereas first order logic, apart from dealing with facts, it can also deal with objects, and also it can relate between multiple objects, and also we can perform some operation or functions on an object. All these things were possible in first order logic. Hence, it is more expressive than the propositional logic. Right. So this is the crux in which we notice that the world is blessed with many objects, some of which are related to other objects, and in which we endeavor to reason about them. Right? So first order logic provides the provision to include objects in the representation of knowledge, and also it provides provision to relate one object with another object, and to perform reasoning. Fine. uh, so anyway, first let us so this is something like a motivation, like why we are discussing first order logic. Propositional logic, or it is sufficient for basic concepts of logic and knowledge based agents, but but whatever we want to express, if it becomes more complex, then in such case propositional logic cannot be used. Propositional logic is too punny a language to represent knowledge of complex environments in a concise way. So which means that it is too weak. It is too weak, or it is too naive to represent knowledge of complex environments. So basically we cannot uh, express what do you call we cannot express complex info using propositional logic. Okay. Yeah, it's weak. We cannot express complex info using propositional logic, and that's the reason why we are moving on to first order logic. First order logic is sufficiently expressive. It is it is it is better expressive. It is quite expressive than propositional logic to represent a good deal of common sense knowledge. First order logic is otherwise called as first order predicate calculus. So this is its another name. It is also called as first order predicate calculus. Sometimes it is also just called as uh, predicate knowledge or predicate calculus. Okay. So these are its different name, right? Predicate or predicate calculus. So FOL is also called as FOPC, first order predicate calculus, or or or, or just predicate logic, or it's also called as just predicate logic. Fine. So without logic, consider without logic. If there is no logic, then generally we represent data. Generally we use data structures to represent facts. Normally, if you take a typical programming language, in any programming language, we use data structures to represent the facts. Say, for example, we want to represent the Wumpus world using a data structure. Then probably we may use a 4 by 4 array to represent the Wumpus world. And a statement of something like this, world of 2, 2 equal to pit, which means that there is a pit in the cell 2, 2 or in the room 2, 2. That's the meaning. So this is the natural way to assert that there is a pit in square 2, 2. If you are using data structures, then we represent it like this, right? But actually, this is not a very what do you call, this is not a very uh, better way of representation, right? This is very what do you call, we cannot call it as domain independent style. It is a domain dependent style. That is, the way of representation is very much tied with the data structures. It is not separated. It is not separated out from the data structures. Okay. But if you consider database systems, DBMS, they were developed to provide more general domain independent way to store and retrieve facts. Whereas data structures, they are not domain independent. They are domain dependent. That is, if you write a program, the program, for a particular program, you will use a data structure. It means the program and data structures were tightly bounded. It is not loosely bounded. So the program is very much connected with the data structures. It's not that you cannot separate out the program, or separating program from the data structures is very, very difficult. But then the drawback in this case is, then for every program you have to create a data structure. Then for every program you have to create a data structure. So so that we call this type of representation as domain dependent. It is not domain independent. The more it becomes domain dependent, then we may have to represent more facts, and it basically it increases the complexity. But compared to data structures, databases are, to some extent, they are domain independent, right? So basically these programming languages, they lack general mechanisms for deriving facts from other facts. So this is the crux here. So when you use a data structures for a particular program, so that data structure is bounded to the program. So they are not able to provide a general mechanism for deriving facts from other facts, right? Each update to a data structure is done by a domain specific procedure. So when something in the data structure is updated, it is done by a domain specific procedure. That is, whatever the program you are using to update the data structure, that is confined to that particular domain. It's not domain independent, right? So why we are discussing this? We are trying to justify like why we are using the why we are studying logics. Because see, because there are certain things which cannot be represented through data structures and databases. Hence, we are using the what you call proportional logic or first order logic, whatever it may be, right? But if you consider proportional logic or declarative in nature, so in proportional logic, knowledge and inference are separate. So this is the key. Whereas knowledge and inference, they are not separate. Whereas knowledge and inference, where they are not separate in databases. Sorry, in data structures. In data structures, the knowledge and inferences are not separate, and hence they are domain dependent. Whereas here, if you consider proportional logic, knowledge is different, inference is different. So they are domain independent, right? And another drawback of data structures and databases is lack of easy way to represent. It's not easy way. There is no easy way to represent. For example, there is a pit in 2,2 or 3,1. There is no way to represent this. There is no easy way to represent this. That is, we want to represent that there is a pit either in 2,1 or in 3,1. How will you represent this in using data structures? So see, even if you use some, so you can say pit is there in 2,2 or in, you can say whether pit is in 2,2 or not. For example, you can say that if there is an array p of 2,2 equal to 1, which means there is a pit. If it is 0, it means there is no pit. Similarly, p of 3,1, you can say that if it is 1, there is a pit. If it is 0, there is no pit. But here we want to say that pit can be either here or here. Now, how do we represent this? So there is no easy way to represent it using any data structures, right? Similarly, if you see this statement, if the umpus is in 1,1, then he is not in 2,2. So if the umpus is in 1 comma 1, so this you may represent using what you call the data structures, that w of 1 comma 1 equal to 1, which means umpus is in 1 comma 1. But this statement itself, it means that when you say that umpus is in 1 comma 1, it means umpus is not in 2 comma 2. Again, we don't have any easy way to represent this. Again, we have to, every location we have to write that umpus is not in 2 comma 2, umpus is not in 2 comma 1. Like that we have to code it. That is a, once you give this statement, it won't automatically take that umpus is not in other locations. Right. So these are some of the drawbacks with data structures and databases. So basically, the data structures, they lack expressiveness required to handle partial information. They cannot handle partial information. You have to inject everything. Propositional logic has the expressive power to deal with partial information. So propositional logic can deal with partial information. How it deals with partial information? Using disjunction and negation. Using disjunction and negation, it deals with partial information. Okay. So here we are just justifying like why we are using logics when already databases and data structures are there in place. The reason is they are not as expressive as the logic systems, right? Okay. Now there is another property of propositional logic that is called as compositionality. So this is another property of propositional logic that is called as compositionality. So what is meant by compositionality? If, for example, if there is a statement like this, yes 1 comma 4 and yes 1 comma 2, so it is related by the meaning of yes 1 comma 4 and yes 1 comma 2. That is so if there is a statement like yes 1 comma 4 and yes 1 comma 2, it is related by the meaning of 1 comma 4 and 1 comma 2. So what is 1 comma 4? So say for example, yes 1 comma, or say here say yeah, so actually this symbol yes we have not discussed previously, so it may have some meaning, right? So say for example, instead of yes, let us assume b 1 comma 4 and b 1 comma 2. So this is related by the meaning b 1 comma 4 and b 2 comma 2, right? So it basically means that there is a breeze in 1 comma 4 and there is breeze in 1 comma 2 also, right? So that property is called as compositionality. That is, multiple individual properties can be combined to form a single property. So that ability is called as compositionality. So that feature is available in propositional logic, right? But what's the drawback with propositional logic? Propositional logic lacks the expressive power to describe environment with many objects. You cannot include objects in propositional logic. So that's the issue, right? So if you take DBMS or data structures, they don't have expressive power to deal with what you call domain independent knowledge. Even DBMS, to some extent, it is domain independent, but data structures, it is purely domain dependent. Hence, we are interested in logic. So if you consider propositional logic, using propositional logic, we can also represent partial information by using disjunction and negation. But partial information cannot be represented using data structures, right? And propositional logic has another property called compositionality, by which multiple individual properties can be combined to form a single meaning. And the drawback with the propositional logic is it cannot deal with objects. Okay. So for as propositional logic cannot deal with objects, you have to write individual. We are forced to write separate rule about breezes and pits for each square. Right? If it has the ability to deal with objects, then we can write a we can write a generic statement. but now that's not possible with propositional logic. For every cell for breeze you have to write something like this. Okay, fine. So this is the reason. So what we discussed here is why we are going to FOL. So why we are going to FOL? Because things cannot be done with data structures or DBMS or propositional logic. Propositional logic to some extent it's okay, but still you cannot represent objects and other things. Hence we are moving to FOL, right? So before discussing about first order logic, let us try to understand the language of thought. This is the human language, whatever the normal natural languages that we speak in the day-to-day life. So we'll have a brief discussion about this. So the natural languages, whatever we speak, like Hindi, English, or Telugu, whatever it may be, they are very expressive indeed. Actually, they are very expressive. But the drawback with natural language is they also suffer from ambiguity, a problem of representation language. So what is the ambiguity? Sometimes sometimes one word can correspond to two thoughts, and thoughts can't be words. Sometimes one word can correspond to two thoughts. Sometimes one word may represent two meanings. The actual meaning may vary with respect to context. Okay. The actual meaning may vary with respect to context. Okay. For example, spring, if you see spring, it may represent a season. Okay. Or it may represent the what you call the spring which is used to move things up and down, right? So it may represent that also. So for what for in so what do we mean? That actually varies with the context. So 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 in such cases, actually natural languages create ambiguity because the meaning actually changes with the context, right? And uh, and there is a scientist or a researcher, Safir Wolf, and his hypothesis claims that our understanding of the world is strongly influenced by the language we speak. That is, we understand the world, or we see the world based on the language that we speak. Okay, so this is what Orff in 1956 he has wrote about how we perceive the world based on our language. So we cut nature up. He says that we are cutting the nature up, organize it into concepts, and ascribe significances as we do, largely because we are parties to an agreement to organize it this way, an agreement that holds throughout our speech community and is codified in the patterns of our language. So basically, what does it mean? It means that, say, you take one language, English. So if you take English is seeing nature in one particular way. So that it says that we cut up nature. We cut up nature and we organize it into concepts, right? And we cut nature in one style. For example, if you take English cuts the nature. The nature is nothing but the world, whatever we see in the whatever we perceive. We we cut the world in and organize into concept in one particular style, right? So whoever the persons who are speaking English, they all they are the parties who agree to that organization, right? So uh, so so it is something like an agreement that holds throughout that speech community. So so internally they all see the world like that only, or they all cut the world and organize the world in that style. For example, if it is Hindi, so they also cut the world and organize the world and organize into concepts, but their style of cutting and organizing may be different. And whoever speaking this Hindi, they all agree to that style of cutting and organizing the concepts, right? So so knowingly or unknowingly it happens, right? So that's what this researcher claims, that whatever the language we speak, actually that influences our understanding of the world, right? So it's quite philosophical, but I wanted to give a feel of that. Okay, so there are some more examples about the natural languages and its ambiguity, or how the language can influence the human's thinking process. For example, in French, there are two words, chaise and fauteuil. Both these words actually they refer to chair, but actually in English there is only one word, chair, right? But later English speakers, they, as a equivalent to this fauteuil, they created one more word which is called as open armchair. So basically, in French, this represents open armchair. This represents a normal chair. Right? So these are something like how our thought, how the language influences our thought, right? So basically, it means that in an English-speaking country, when somebody says chair, what do you think? What's the mental image you are creating, right? Probably you'll think of a chair with a normal chair, right? But uh, but but in case of French, there are two things, two words are there. So each represents a different kind of chair, and accordingly, their mental image will be different. Okay, so that's the point. Similarly, here is another example. So in Australia, there is one particular community who speaks this language, Aboriginal language, Gu Gugu Yimthi or something, right? So in this language, they have no words for relative directions. They have no words for relative directions such as front, back, right, left. It is this particular language. This particular language, it does not have words for front, back, right, or left. So they, to use these directions, they use only north, west, east, and south, right? So instead, they use absolute directions. For example, I have a pain in my north arm. So I have a pain in my forearm or in my front arm. Instead of that, they say like I have a pain in my north arm, something like that. And if you see, for example, in bridge is considered as masculine in Spanish, and it is considered as feminine in German. Right? So these are, we are just discussing something like how the language can influence our thought patterns. Right? Fine. So FOL, what it is going to do? It is going to combine the best of the formal and natural languages. It is going to combine the best of the formal. Formal is proportional language. It is going to combine the best of the proportional and natural language. Okay. So what is the best part of the proportional language? The proportional logic. Proportional logic is declarative, right? That is whatever it represents facts, and the fact can have take either the value of true or false, right? And propositional logic, it has compositional statements that is context independent. It has compositional statement that is context independent, and it's unambiguous, right? So at the same time, we should also borrow ideas from natural language. At the same time, uh, FOL is a combination of then propositional logic plus natural language. That is, it should borrow ideas from natural language by avoiding its drawbacks. Its drawbacks are like sometimes it creates ambiguity when multiple words refers to the same thought. Okay. So in FOL, we include objects. So using FOL, we can represent objects. So objects may be people, houses. These are some examples for objects: people, houses, numbers, theories, uh, Ronald, colors, so on and so forth. Relations. So relations are something which connects multiple objects based on a relation, and these relations can be of two types. They can be unary relation or n-array relation. And unary relation is otherwise called as property. Right? A unary relation is also called as property. For example, an object may be red in color. So that is also a relation, but that is called as unary relation or a property. Or an object may be round. So that is also a relation. So unary relations are also called as properties. And also we have n-array relations, such as brother of, bigger than. So here we have in a unary relation is applicable to a single object, whereas n array relation is applicable to more than one object, right? And also it includes functions like father of, best friend of. So when you can apply some functions on an object. So when you apply functions on an object, it will return some value. For example, father of x, if x is equal to someone, father of x will return some value. So whoever the father of that person. So these kind of, so basically what we are discussing is FOL allows this type of representation. It allows logic, sorry, it allows objects, relations, and functions, right? Almost any assertion can be thought of as referring to objects and properties or relations. So any assertion can be made by through any assertion can be made through objects, properties, and relations. So which means that any assertion can be represented through FOL. So here are some examples. Let us take this statement: 1 plus 2 equals 3. Right now we are not going to FOL, but for this statement, let us see what are the objects, relations, and functions. So the objects are 1, 2, 3, 1 plus 2. These are the objects. Okay. So you may wonder 1, 2, 3. Okay, how this 1 plus 2 comes? Let us discuss that. Relation. What is the relation? Equals is the relation. Equals is the relation. So it is as if equals is a relation. You are applying the relation equals on 1 and 2. Okay, when you apply the relation on when you apply the relation equals on 1 and 2, what you get is 3. What you get is 3. But 3 can be otherwise called as 1 plus 2. But 3 can be otherwise called as 1 plus 2. Okay. So these two are objects which we got after applying on this function. Right. These three are the objects which is available in the input itself. 1 plus 2 it is available. Okay. 1 plus 2, 3 is also available. But this 1 plus 2, how we got? Because when you apply 1, 2 on equals, you get, sorry, not equals, plus. When you apply 1, 2 on plus, this function plus, you will get 3. Okay, you'll get 3. And this 3 can also be called as 1 plus 2. Okay. So equals is 1 plus 2 is equal to 3. Right? 1 plus 2 is equal to 3. To represent that, we are using equals, right? So equals can be represented like this: equals of 1 plus 2 comma 3. So which means that 1 plus 2 equals 3. Right? Okay. So 1 plus 2 is a name for the object that is obtained by applying the function plus to the objects 1 and 2. 3 is another name for this object. So this whatever. So when you apply plus on 1 and 2, you get 3. 3 can also be called as 1 plus 2. So here is another example: squares neighboring the umpus are smelly. Here the objects are umpus and squares. Property is smelly. So what is a property? It is a unary relation, that is a property. So squares adjacent to umpus are smelly. That square is smelly. That's it. It is applicable only to one object. So it is called as property. Relation, neighboring. Squares adjacent to umpus or are called as neighbors. Right? Squares neighboring the umpus. So this neighbor is a relation. Evil King John, it is another example. Evil King John ruled England in 1200. So the objects are John, England, 1200. 1200 is also object. Relation is ruled. Relation is ruled. So it is something like this: ruled of John, England, 1200. It means John ruled England 1200. Okay, but John has some properties. What are his properties? He is evil and also he is a king. Right? So the properties are evil and king. Okay, fine. So basically, first order logic is built around objects and relation. First order logic can also express both And another important thing is first order logic can express about some or all of the objects in the universe. So this is important. So this feature is not available in propositional logic. So so probably you might have learned previously, for some we use existential quantifier, and for all we use this universal quantifier, right? So we'll be discussing probably later. So I think we'll represent like this E. Yeah. So first order logic can also be used to represent facts using some or all of the objects in the universe. So this enables us to represent general laws, such as squares neighboring the umpus or smelly, right? So these general things can be represented using some or all the using the mechanism to represent some or all of the objects in the universe, right? So so this feature is not available in propositional logic. In propositional logic, if you want to specify squares neighboring the umpus or smelly, actually you would write for every square, but that is not required when you use FOL. We can just write as one rule by using this existential or universal quantifier. Okay. So the primary difference between propositional and the first order logic lies in the ontological commitment made by each language. So what is ontological commitment? Ontological commitment, in the sense, it represents like what the language assumes about the world. That is called as ontological commitment. What the language assumes about the world, that is called as ontological commitment, right? uh, so there is another thing, uh, there is another difference between propositional logic and first order logic, that is epistemological commitment. So what is epistemological commitment? So the epistemological commitment, it represents the states of knowledge that it allows with respect to each fact. The I mean, so basically it means that the whatever the knowledge, uh, whatever the whatever the logic we are using, what type of uh, states of knowledge it allows for each of the fact. Okay. So ontological commitment, it represents like what uh, the 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 language, whatever the language we use, the language can be either first order logic or propositional logic or whatever it may be. So currently we are talking about FOL. So what kind of things the language supports, that is called as ontological commitment. For example, if you take propositional logic, it supports only facts, nothing else. If you take FOL, it supports facts, objects, relations. So what and language supports, that is called as ontological commitment. And epistemological commitment represents what these languages will what values these languages can hold, what values these languages can hold. So that's what epistemological commitment says. So this uh, table will make things clear. For example, in propositional logic, ontological commitment, what exists in the world, it's only facts. And epistemological commitment, what an agent believes about facts. So the facts can be either true, false, or unknown. Okay. In first order logic, if you see ontological commitment, so basically it represents what exists in the world. What exists in the world, facts, objects, and relations. And epistemological commitment is the agent believes, what the agent believes. Again, it can be either true, false, or unknown. So there is another logic called temporal logic, which is the next level of first order logic, which is apart from facts, objects, and relation, it also includes time. And here the epistemological commitment is true, false, or unknown, right? Here the time also comes into picture. That is, certain fact can be true in a particular time, but it may not be true in other time. Okay. And if you see probability theory, it includes only facts, and it includes degree of belief. It takes values between 0 and 1. Okay. So this is probability of belief. So probability, basically, we assign some belief based on the experience, based on the past experience, or whatever it may be, right? There is another logic called fuzzy logic, which is facts with a degree of truth. This also takes values between 0 and 1, but these two things are different. Okay. For example, mm, if you say Ramu is tall, in fuzzy logic, Ramu is tall can take a value of 0.7, which means that he's which means that the degree of truth of this statement is, this is the degree of truth. The truthness of this statement is 0.7. Okay. So this is, probability is different. Probability talks about degree of belief, right? So maybe how we got that belief based on the past data, or uh, or whatever it may be, right? Or if it is a coin cause, if it is a coin tossing, then we know that the probability of success is 0.5. Or if it is a throwing of die, we know that the probability of success is 1/6, right? So whereas this fuzzy logic is degree of truth. Say for example, there is a glass, and the glass is filled with half of water, right? Okay. Now I'm saying that this glass is filled with water. This glass is filled with water. Now if you use fuzzy logic, what is the, how this statement is true or not? This glass is filled with water, this statement is true or not when you use fuzzy logic? Actually, you can give some value like 0.6. So if it is 60% full, you can give the value 0.6. So this statement is true, but its degree of truth is this much. So that's what fuzzy logic discusses about. Okay, fine. Let us stop here for today's discussion. We'll continue further. Thank you.